Yeah, nice. So I'll just post back the link for the notes. It is right here. Uh, okay, and now today so a recap for last week first. Last week we talked about computational complexity, and then we talk about big O notation. We have this function count as the number instructions, and then we have this thing, and then we talk about complexities, asymptotic notation. So we have the big O notations, big omega notation, and big theta notation. And then we say that we basically just ignore the coefficients and we only look at the largest degree. So given, like, for example, yeah, okay, it's like for example, for any polynomial functions fn, then we have the O of fn is equals to nd, where the d is the degree of the polynomial, which is, yeah, which is that. Then next we talk about some interpretations. So we see that like if you have n cubed, then your largest n that you can get to, if you want to finish within a second, and so you need to n to be 1000. Otherwise, it probably takes a long time for you to finish it. So this asymptotic complexity is very useful for us to know how to estimate the runtime. Yeah, and yeah, so now we can get back to our number theory part, which is the Euclidean algorithm. So we have previously we were talking about computational complexity. The reason for that is I want to motivate the reason. I want to give a good reason on why do we need to study this Euclidean algorithm, and the main reason is because Euclidean algorithm is a very fast algorithm to find the GCD of two numbers compared to just factoring itself. And this fastness is determined using big O notation. Okay, so in the previous 2 weeks, we talk about how we rely on this property. GCD of A and B is equals to GCD of A and B plus A. And then we prove it halfway, and we didn't actually prove it. We just proved like a part of it. So now I'm going to reprove this with more rigorously. So now I let G to be a GCD of A and B, and I want to prove that GCD of A and B is equal to GCD of A plus A and B plus A. By definition of GCD, we have that G multiplied by K1 is equal to A, and G multiplied by K2 is equal to B. So because this is a greatest common divisor, right? So G divides A and G divides B. This will implies GK1 is equals to A and GK2 is equals to B. So for example, if you are looking at GCD of 3 and 6, so you know that this is 3, right? Then you can write this to be 3 multiplied by 1 is equal to 3, 3 multiplied by 2 is equal to 6. So that's the greatest common divisor that we have. So how do we prove this? First, we see that if we add A and B together, then we can write it in terms of GCD of A and A plus B is basically G multiplied by K1 plus K2. So because this was GK1 plus GK2. So you can just factor out the G, and then you can get this part. So this basically implies that A plus B has a factor of G. So GCD of A and A plus B must be greater and larger than G, because we know that G divides A and G divides A plus B. So the GCD of A and A plus B must be always greater than G. But we want to show that this is exactly equal. How do we do that? So now we write G to be equal to A plus B, and then we sort of restructure it. So we add A here, and then we minus A here. So it is basically the same thing here. And then you notice that what I showed previously is that I can take so I have AB, right? GCD of AB. I can take this term, I add to here, this become this will become GCD of A and A plus B. You see that this is always larger than or equal to. That is what I show here. So sorry, it should be the other direction. I think should be the other direction. Okay. Yep. So right here we have GCD of A and A plus B is larger than GCD of A and B. So we can just write this in terms of something like that. Then you can see that this is basically just you can add this part to here. Then okay, actually I think I should write the other parts here. Let me just clean this up first. Okay. Yeah, I think I forgot to write one line here. So GCD of A and A plus B is larger than G. We can also prove that GCD of A and A minus B, sorry, B minus A, is larger than equals to G. So how do we prove this? This is just directly applying this, right? Because B minus A is equals to G of K2 minus G of K1. So this would be just be G of K2 minus K1. So we also have this thing. I forgot to write this down. So this is also quite important to for our proof. So you see that here, right? We can take this as B, and then this is basically if this is B, right? Then this is GCD of A and B. So you can just think of B as a variable. So if you represent this as B, right, then you will see that this thing will be larger than this. So why is this the case? It's because we have the, so this is basically this B, and then the minus A is here. So you see that if I replace my B to be this B, then I will get this inequality. So is that clear? I basically just replacing A plus B as one, maybe a bigger variable B, and then this will become B. So this will become B. So I just look at A plus B as a single entity. So when I do that, then I will get this inequality. G and A plus B minus A is larger than equals to GCD of A and A plus B. Now this part is, so this inequality here is exactly this. We know that GCD of A and A plus B is larger than G. So this is basically just these two. This and this are just these two. So what we have proved in the end is that we prove that GCD of A and B must be larger than GCD of A plus B. A and A plus B must be also larger than GCD of G. So this forces everything to become G. So here, this will become G, this will become G, and this will become G. Because I'm saying that X, G is larger than equals to X and larger to equals to G. So this implies that this thing must be G. Because I can never be larger than or equals to, like the only value possible here is G. So that is exactly what I am proving here. At the very front of the inequality, I have G here. At the very end, I have G here. So I am forcing this part to also be G. So which is why we will get in the end, GCD of A and A plus B is equals to G. So is this okay? Okay, nice, great. Any questions? Yeah, in some sense it's quite abstract, but I think you don't really need to understand the proof that much. So you just have to accept this thing, which is basically you however add it, however do it, it will always become the same. Okay, So now the next thing is, this property is quite good, right? Because we can always, okay, so let's say like we can always write something like this. We can always write GCD of A and B is equals to GCD of A and B minus with some multiples of K. Because we know that GCD of A and B is equals to GCD of A and maybe B minus A. And then this thing you can repeat again, you can minus this again, and then this will get GCD of A and B minus 2A, and so on. Then you can get GCD of A and B is equals to GCD of A and B minus KA. So we can take K to be the maximum integer such that B minus KA is non-negative, which is basically just the remainder operation. So so what I'm saying here is that we can this thing is basically A modulo it's basically B modulo A. So I try to divide B with A, then I get this thing to be K. So this will become KA, and this will be B minus KA, which is basically the remainder. So I can do something like this. So I get K to be the maximum integer such that this thing is non-negative, which is basically the remainder. So this is a very long-winded sentence, but this is basically just remainder of B divided A. So a bit of examples. Let's look at this example. Example 35. So we have GCD of 3 and 5 is equals to GCD of 3 and 2, because we can this is 5 minus 3. And then this is then GCD of 3 and 2 is equals to GCD of 1 and 2, because this is 3 minus 2. And then you can repeat this again, then you get 2 minus 1, 2 minus 1, 2 minus 1 multiplies by 2. Then you get that the final GCD is 1. So you see that 3 and 5 is prime number, right? So of course their GCD is 1. And then 3 and 2 is also 1. So this equality actually holds. Another example is this. So look at GCD of 10 and 7. We know that 7 is a prime number. 7 cannot divide 10. So this is 1. But you can walk through the process. Then finally you can get the GCD of 1 and 0. And this implies that it is equals to 1. So for 6 and 5, for example, we know that 6 is 3 multiplies by 2. And then this is 3 multiplies by 5. So the greatest common divisor here is 3. And then you can also walk through the process and this will become 3. So before that, I just want to mention this thing. GCD of A and 0 is always equals to A. Reason being that we define GCD as the greatest integer G such that G divides A and so GCD of A and B is equals to the greatest integer such that G divide A and G divide B, right? But what does the divides here mean? Divides here basically means that I have some K multiplied by G is equals to A. So then we have a simple identity that every integers will divide 0. Because A multiplied by 0 will be always equals to 0. So any integer will divide 0. So GCD of A and 0 will always be A. So it kind of seems a little bit unintuitive because you see that, okay, 3 divides 0. It sounds very weird, but by definition, this makes sense. Okay, so yeah, this inspires an algorithm to find the GCD of two numbers by reducing these two numbers repeatedly. So you see, I keep reducing one number with another. I try to make these two numbers smaller and smaller and smaller until they finally become 0. One of the number becomes 0, and then the other number will be my GCD. So that is the algorithm that we are trying to have. And this is the Euclidean GCD algorithm, which turns out to be extremely simple, and indeed it is. So basically what we are doing now here is that we have A in each step, right? I have B is equals to A modulo B, and then A will become B. So if I write this now, the new A will become B, and then the new B will become A modulo B. So A modulo B is essentially equals to A minus KB. And then we know that GCD of A minus KB and B is still equals to GCD of A and B. So here, let's look at the analysis. The correctness of this algorithm is clear with Lemma 4.1, which is basically how we can just add a multiple of some numbers and the GCD will remain the same. So new A is set to B and new B is set to A modulo B. And A modulo B means the remainder of A after divides B. So this is just A minus KB, where K is the largest positive number such as this thing, host. So we have GCD of A, B is equals to GCD of BA, and GCD of BA, you just add it with the multiples of K. So this is what you get in the end. So in the end, you always get you repeat this iteration how many times, right? No matter how many times you repeat this, A and B will always have the same GCD. So now, okay, that is nice, but we need to prove that this algorithm will end, means that it will terminate. Because what if B never gets to 0, right? If B never gets to a number lower than 0, then this will become an infinity loop. So we need to check the algorithm terminates. And it is not too difficult to see that because every time when you do the modular operations, the integer will always get smaller and eventually drop to 0. Why? Because if you do modulo A, right? So if you do B modulo A, then B is guaranteed to be less than A. Because if you do remainder divide A, then the remainder will always be less than A. So that's the thing. So the numbers will eventually get smaller and smaller and smaller until the algorithm ends. So now the next question is, how many iterations will this perform? So this is the analysis of the complexity part, because it is not that clear that this will end that quickly, right? What if so what's the complexity of this? So you could run this for many times, right? But how many times is the exact question that we want to answer. So now we try to analyze it, and we see that the runtime of the algorithm is actually log of max of A and B. So why is that the case? So you see that in each step, right, we look at B. If B, okay, so there are two cases. So this is case 1. This is case 2. If B is smaller than or equals to A divided by 2, right, there can only be two cases, right? Because one is that you are smaller than this, or the other one is that you are larger than this. So if you are smaller than this, then A modulo B, you always be smaller than. So A modulo B will always be smaller than this thing. So this thing will be decreased by at least half of the size of A divided of A. So this thing, so A modulo B will be at least half of A already. And in the second case, if B is larger than A divided by 2, then A modulo B will always also be decreased at least half, because if B is larger than A divided by 2, then A modulo B is essentially just A minus B, because you can't put a larger K. If you put A minus 2K, right, this will become a negative number already. So the largest number you can put here is 1, which is A minus B. So this thing, if you minus something, right, then you can see, like, okay, so if this is A, if this is A divided by 2, this is B and this is A, then if you take A minus B, this length will be short, and it will be at least twice shortless than the original length. So what we basically prove is that in every step, one of B or A will decrease by at least half. So if you decrease by at least half by in every step, then means that we have this log factor already. Because what we are trying to see is that how many times we can divide by 2 such that these things will become 1. So this factor here is basically, the K here is basically log of A. So because we are also not sure whether A is larger or B is larger, so we just take the maximum of this. So the final complexity that we get is log of maximum of A and B. Okay, any questions? Great. Okay, good, nice. Okay, so compared to factoring that we have previously, so we know that this factoring algorithm here is this thing. So compared to factoring numbers, then find the GCD by looking at the factors, this is a much faster way to find GCD. And Euclidean algorithms does it very well. So now, after looking at Euclidean algorithms, then we can state Bézout's lemma, which is sort of a very simple extension of Euclidean algorithm, which is also quite direct to prove. So we have let a, b to be 2 integers, and then GCD of a, b is equal to g. Then what I claim here is that there exists y, x and y such that ax plus by is always equal to j. So an example here is that okay, maybe I don't really have an example. Oh yeah, I can just make out an example. So like for example, we know that 3 and 5, GCD of 3 and 5 is equal to 1, right? Then I can write 3 multiplied by 2 minus plus 5 multiplied by minus 1. And you check that this thing is equal to 1. Because the GCD of 3 and 5 is equal to 1, then we can always find x and y such that ax plus by is equals to 1, which is the GCD. So this is one example. And then you can check for every possible pairs A and B, this will always work. So how do we prove that? How do we prove this property? So the way that we prove it is we look back at Euclidean algorithm itself. So recall that in each step of Euclidean algorithm, we are performing B1. We write B1 is equal to A modulo B. And then this basically says that I just minus KB. And then I swap A1 to become B. So after one step, right, my A1 will become B. And then my B1 will become A minus KB. Then I continue the algorithm again. Okay, I continue again. Then now I check what is A1 modulo B1. So A1 here is B. And then B1, modulo B1 means that I try to find the greatest divisor. So I write K1 K1 multiplied by B1. So this will become B minus K1 multiplied by B1. And then what is B1? B1 is this, which is basically A minus KB. And then you just rearrange it. You see that B2 in the end is equal to A multiplied by K1, negative K1. So this term, we get it from here. And then B multiplied by 1 plus K times K1. So K and K1 from here, and the 1 is from here. So I just factor out the terms, then I'll get this in the end. So this is essentially just another X, and this is also another Y. And then we can see that no matter how many steps that we do, we can always express. So you see the first A1, B1, A2, B2, it can always be expressed as A multiplied by something plus B multiplied by something. So this is always possible. And the reason is because we are just deducting something with a multiples of that thing. And then so in the end, I'm just playing around with this original A and B and so on. So what happens in remember that towards the end of the algorithm, we always have one term to become 0. You see, if this is not 0, then this algorithm will not end. So in the at the very final end, right, we always have one of the term becomes 0 and the other term is the exact GCD of that term. So A of the last iteration, A will become the GCD of A and B, and then the B will become 0. So this thing I can just, because we already show that in every step it will always be some multiples of K of A plus some multiples of B. So there must exist an X and Y such that this thing holds. Okay, so any questions? Okay, it's good. And then if you have anything, yeah, if you have any questions, can just ask. Right. Three, yeah, 3-0 will terminate the loop. The reason is because the condition here is B is larger than 0. So if B is equals to 0, which is 3-0, then this will terminate the loop. And you know that when we do modular operations, right, the remainder will always be greater than larger than 0. So if my condition here is larger than 0, then means that the B must be equal to 0. This must always be true. And then if B is equal to 0, the GCD will become A. So because in every step, the every step of A and B can always be represented by some multiples of K, some multiples of A plus some multiples of B. So with that, we have our Bézout's lemma, which is that there exists an X and Y such that this is true. Okay, then I'll move on. Yeah. It's good that if you can refer back to the things. So that's why the link should be quite useful. So now we can introduce the extended Euclidean algorithm, which is basically the questions on how do we actually find this X and Y. So we know that there must exist an X and Y such that AX plus BY is equals to the GCD of A and B. But how do we find this X and this Y? The way that we do it is we just modify the Euclidean algorithm by a little bit. So we basically keep track of the intermediate X and Y, Xi and Yi, like what I do here. I keep track of the intermediate X and Y. And then if we do this, then this will basically just call the extended Euclidean algorithm. It is quite a simple modification, but basically you see we have this Q, which is the quotient, A divided by B, the quotient. And then in this step, I just keep track of the operations here. But yeah, you can check that this is correct. So x0 initially, x0 and x1. So initially we have A and B, right? So A is basically 1 multiplied by A plus 0 multiplied by B. And then B is basically 0 multiplied by A plus 1 minus multiplied by B. So my initial x0 will become 1 and this one will become 0. And then y0 is equals to 0 and y1 is equals to 1. So this is what we had initially. And then I just want to make sure that after every step, my x0 and x1 is updated to the correct value. So how do we check the update? So we just like so this thing is just swapping, right? Because we know that the new so we know that A will become the new A will become the OB. So I just swap the x1 to become x0. So here we have this thing will be equals to this, and then this thing will be equal to this. And then the other one is just x0 multiply minus q, which is the quotient of a divided by b here, and so on. Right. So with that, then the final result that you get here is a, x0, and y0. And then you can check that x0, a plus b, y0 is equals to the GCD of AB. Well, you don't really need to understand the details on this, but I believe knowing that it exists and then we can use the extended Euclidean algorithm to find it is enough. So I remember in my exam for number theory course in uni, they asked us to manually write out the solutions. So like, for example, find out, so for example, all these questions. So you have to do it on paper. Okay, so yeah, this is very interesting because we can solve all these questions. We want to find integer xy such that 3x plus 5y is equals to 100,000. So how do we do this? I'll just show you one example. So we know that there exists 3x plus 5y is equals to GCD of 3 and 5. This is equals to 1. Then I just multiply this by 100,000. And multiply both sides by 100,000. Then my new x and new y is basically I just bring this term inside. So this will become 100,000. That is how you find the integer solution of 3x plus 5y is equals to 100,000 by using extended Euclidean algorithm. So the next question, can we find x and y such that 4x plus 8y is equals to 1? So you see that it might not be possible. We know that GCD of 4 and 8 is equals to 4. And then we know that there exists x and y such that this is true. But can we find x and y such that this is true? So the answer here is that there is no integer x and y such that this is true. It's impossible. Reason being that if the GCD is 4, right, then I can always take 4 out. So no matter how 4x plus 8y is, right, I can always take 4 out to become 4x plus 2y. So this is an integer. This is also an integer. So the result here must also has a factor of 4. That's why if you have 1, right, 1 does not have a factor of 4. So yeah, unless you allow decimal, but here we are only looking for, we are only interested on integer solution. So which is basically saying that there is no integer solution for this identity. Then in some sense, right, you can see that if you have ax plus by is equals to something, some positive number, the lowest it can go is ax plus by is equals to g. Lowest positive number. Larger than that positive number, you can never do that. You can never get that. And then now let's look at the example 30. So this is basically the same thing. 3x plus 6y, you can find something that's equals to 3. And then 3 multiplied by 4, then you get 12. That is okay. And then the final example, x and y such that this thing holds. So it might seem very complicated, but you just need to find whether GCD of 97 and 6237 is equals to 1. And we know that 97 is a prime number. So if 97 does not divide 6237, then this thing will always hold. Then we can always find such an integer x and y. Okay, I hope this is clear. Any questions? I think, yeah, so this Bézout's lemma, sometimes it kind of appears in crypto questions in CTF. Usually it hides, yeah, if you see that something like a multiplied by x plus some b multiplied by y is equals to something, then you can just use extended Euclidean to solve this. Extended Euclidean algorithm is supposed to just be able to check if it's valid. Yeah, it can help us to check whether it's valid and also give us an solution. So because if like, yeah, so how do we know that it's because we have this property. I did not prove this, but ax plus by is equals to g. This is basically the lowest positive number that you can get with ax plus by. Yeah, then you just, if you want to check whether you want to find a solution, like for example this one, then you just multiply by this divides the term here divide by the GCD. Then you can get a solution to this equation already. Yeah. So it is not fun to solve it by hand, but you can do it. But since we have computers, we just use code to do it. We just know that this is possible, and then somehow have the idea on this can work, then everything is perfectly fine after that. Yeah. Also, I want to talk about one very interesting thing before I move on to modular arithmetic. So if we have p, right? So this is a prime number p. P multiplied by x plus some a multiplied by y. So if I have the condition that a is smaller than equals to 1, I'll put 1 here, and then this is strictly smaller than p. So what happens is that we know that GCD of a and p will be always equals to 1 because this is a prime number. So p here is a prime number. Then for all possible a, we can always have solution of x and y such that this identity holds, which is very useful in modular arithmetics laterwards. And yeah, so if you have if the GCD of these two numbers is 1, right? Then so if GCD of a and b is 1, then for any equation, for k, right? For any a, any k, you can always find an x and y. For any k, you can always find a solution. Integer k. Because you can just multiply the x and y to be k. You can just multiply k, and then that k will be absorbed inside x and y itself. And in other words, if this thing is not equals to 1, right? If this thing is equals to, let's say, g, then these things, then k, the solution will only exist if g divides k. If g divides k, then solution exists. because one divides everything, right? So in some sense, you can also use this idea to somehow like get the intuition of what kind of or what solutions do we have with this thing. Okay, so yeah, now I will just briefly run through modular arithmetics. So the reason that I introduced Bézout's lemma and extended Euclidean algorithm is because we want to do modular arithmetics, and modular arithmetics will use this thing. So yeah, okay, now I'll talk about this. Before that, any questions? Okay, then I'll just briefly run through modular arithmetics, the part that I want to talk about today. Okay, so why do we even do modulo, right? So the biggest reason is because we don't have infinite amount of memory. So we cannot do everything in real number, but real number has a lot of nice property. So we want something to also have very nice property that real number enjoys, but finite memory. So modular arithmetic is a very great is a good candidate for this kind of situation. So I have already mentioned this before, but now I'll just like reintroduce it. We have congruence. So for any three integers a, b, and m, we say that a is congruent to b modulo m. We can write it as something like this. So this is basically we say this. So how do we read this? We say that a and a is congruent to b modulo m. So this thing we write it down like that if and only if a minus b is equals to km for some integer k. So basically what I'm saying is that a modulo b, so the remainder of a divides after dividing by m is equals to the remainder of b after dividing by m. So how do we see this? Is because a modulo b or a modulo m is equals to a minus k1m, b modulo m is equals to b minus k2m, and then this thing we have that these two things are equal, right? So if these two things are equal, then these two things are equal. So I just bring this down. So these two things are equal. So I just bring this down. Then I move this to one side. Then I get a minus b is equals to k1 minus k2 multiply m, which is basically our definitions. So it might sound a little bit fancy, but it basically says that I move this to here, and then a minus b, this thing m must divide it. Yeah. So modular operations have a lot of nice property. So the first one is that it respects addition. We can perform modular operation first, then we add them. It is equivalent to add them, then perform the modular operation next. It is the same for multiplication, negation, additive identity, and multiplicative identity. So basically, you do remainder first, or you do addition and multiplication first. It doesn't matter. The order doesn't matter. So why is this the case? So we just prove we show the proof for these two property. The other one you can just do it yourself. So a modulo m and b modulo m is equals to a minus k1m and b minus k2m. So I add these two terms together. This will becomes a plus b minus these two become together. And then I move this towards the other side. Then a modulo m plus b modulo m minus a plus b is equals to k1 plus k2m. And by definition, this will basically say that a modulo m plus b modulo m is congruent to a plus b modulo m. So for the multiplication here, it's basically the same proof. So I just multiply this thing, and then this multiply together will be somewhat messy, but it is still the same. So b1k, bk1 and ak2, k1, k2, we have this. and then you just move to the other side, and you also just get the same thing. Oh, sorry, this is a typo. This should be multiplicative. Yeah, this should be times. Okay, so yeah, this is nice. Modular operations have this very nice property. But the question now here is that, can we do division modulo? So let's look at an example for this. Suppose we have this property, right? We're not sure, so we're not sure whether this is true or not. So now let's check. Let's say we have m is equals to 7, which is the modulo. And then we have a is equals to 15 and b is equals to 3. Then 15 modulo m, this one will be 1, because 7 times 2, 15 minus 7 times 2 is equals to 1. B modulo m, 7 divided by 3 divided by 7, this will just be 3, because 3, you just write 3 as 3 minus 7 times 0. And then if we do the other side first, if we do a divide b first, then 15 divided by 3 will become 5. Then 5 modulo 7 will also be equals to 5. Then if this is true, right, then we will have that 1 divided by 3 is equals to 5 modulo 7. But here we have a problem, right? So modulo, we have always been working in integers, but 1 divided by 3 is not an integer. This is a rational number. How do we even say this? Like I can't, like, if you put it inside the definition, back to the definition itself, right? Maybe you can write that 5 minus 1 divided by 3, and then you want to check whether this is equal to k7, k multiplied by 7. But this does not make sense, because this thing itself is already a rational number. It is not an integer, but this thing is an integer. So you can never have an integer to become a non-integer. So this thing will never hold. So then what does this 1 divided by 3 actually means? But although it doesn't really make sense, right? However, we see that if we multiply 3 on both sides, so here I multiply 3 on both sides, then this side will become 1, this will become 15. And then 15 is actually, modulo 7 is actually equals to 1. So although at the division sense, in the usual division sense, doesn't really work out well, it doesn't really mean that much. But then if you multiply both sides with that, with the value is with the divisors, with the denominator, then it sort of works out a little bit better. Yeah. So okay, so this inspired the definition of modulo inverse. So instead we want to try and define this better. So how do we do that? So we do modulo inverse by saying that for any two integer a, m, the inverse of a modulo m is an integer b such that a multiplied by b is equals to 1. So if a multiplies by b is equals to 1, then this is nice, right? Because we can sort of like saying that you multiply these two things together, then you get back the identity 1, which is nice. So let's write, then in some sense we can write b as a to the power of -1, or 1 divided by a. So this is not usual rational number. This is not rational number. This is some kind of new definition. So don't think about it as the usual natural numbers. This is a total new thing. So then we can say, okay, if we have this definition already, then we look back at this example. We can say that 5 inverse is equals to 3. Reason being that, 3 inverse is equals to 5. 3 inverse is equals to 5. Reason being that if I multiply both sides with 3, then this will becomes 1. Okay. So okay, so far any questions? Sometimes to avoid confusion, right, we'll try not to write it as 1 divides by a, because it kind of makes things a little bit messy, and we write it in terms of a to the power of -1. But it basically says the same things. So I'll just finish out what I want to talk about today. Then maybe I'll skip this part. Wait, these two are the same page. Okay, yeah. Okay, so this is the final thing that I want to say. The inverse of a modulo m exists if and only if the GCD of a and m is equals to 1. And then we can find the inverse using the extended Euclidean algorithm. So why? Okay, if GCD of a and m is equals to 1, right? By Bézout's lemma, we know that there exists x and y such that ax plus my is equal to 1. Then you try and see what happens if you modulo ax plus my. You modulo m, right? Then means that you divide this whole thing with m. Then this term will be cancelled. This term will be cancelled because it is a multiple of m. So in the end, you get ax is congruent to 1 modulo m. And this x is the exact coefficient that you get from Bézout's lemma, from extended Euclidean algorithm. So yeah, so we have this. If you want to prove it, prove this more formally, you can say that ax. Why does ax? Because ax minus 1 is equals to my, and then this whole things, m divides ax minus 1. So we have that ax minus 1 is congruent to 0 mod m. So if this thing is true, then ax is congruent to 1 mod m. Okay, so that is the final thing that I want to say on. And why do we go all the way to introduce extended Euclidean algorithm? Is because without extended Euclidean algorithm, we sort of don't really know how to find the modular inverse. But with extended Euclidean algorithm, this thing can be found very easily. Okay, any questions? Oh, good. Yeah, you can. If you have any questions afterwards, you can also like just PM me on Discord. You can just ask me. So, always okay. So maybe a quick example. Let's say if I want to find 3x congruent 1, modulo 5. Let's say if I want to find this. So basically x is just 3 inverse. Okay. Then how do we find x? The way that we do it is first we write it in terms of, we try to find 3x plus 5y is equals to 1. And then just now we already know that x is equals to 2, x is equals to 2, and y is equals to -1. So 3 multiplied by 2 will congruent 1 modulo 5. And you can check that this is true. In other words, if GCD of A and M is not equal to 1, is larger than 1, then modulo inverse does not exist. So an example is if you try to find 2x is congruent to 1, you try to find the x such that this modulo 8, for example, you'll see that there will not be any x that satisfy this condition. No x will satisfy this condition. Okay, so yeah, so that's all I want to talk about today. Before we end the session this week, any last few questions that you want to ask? Yes, if you want, yeah, I actually consider giving exercise to you to do. If you are interested in doing exercise, then later I'll prepare and then I'll send in the chat. Yeah, in the Discord. Yes, I have exercise. If you want exercise, I can provide exercise. Yeah, I also think so. But I was thinking whether, because this is like very kind of informal, so I was thinking whether whether you all will even try and do it. And then I just feel that, oh, maybe it okay, that's good. Later I'll prepare exercise for you. Okay, so any more questions? Yeah, if not, then I think we can end it now. Feel free to ask me